Hi friends, welcome back to new session. In this session, in DC machines, we'll discuss conditions for buildup of voltage in a self-excited DC generator. I think in the last sessions I explained already. The self-excited DC generator means shunt, series, compound generators comes under category of self-excited DC generator. Okay. Now let me discuss. Let me take in this session conditions for buildup of voltage in a self-excited DC generator. Further, I had taken example DC shunt generator. I had taken example. So by taking a DC shunt generator, now let us discuss what are the conditions for buildup of voltage in a self-excited DC generator. Okay. See guys, here let me take this one as RSS, nothing but shunt field winding. And in this field winding, I just connect some variable rheostat. Let me take this one as RF, variable rheostat, okay. And this is nothing but armature. And let me take this one as a load, okay. And let me, the two had taken here variable load resistance, okay. Now let us see guys, here what are the conditions for buildup of voltage in self-excited DC generator, nothing but in a DC shunt generator. So I take an example DC shunt. To be frank, these points are valid for shunt series as well as for a compound generators also, okay. Let us see first point. There should be a residual flux. First of all, residual flux means what? See, I told you already what is the function of a field winding means. Field winding is the one through which if we send some current, so magnetic field will be produced. Process of sending current through field winding and creating magnetic field is called excitation. So, if you see, if example, if you take a separately excited DC generator, there some separate DC source is connected for the field winding for excitation purpose. Therefore, I don't want any residual flux in a separately excited generator, but in a self-excited generator, you can take example shunt or series or compound any generators. Okay, here since we are not connecting some separate DC source for the field winding for excitation, so to be frank, whatever the current produced in that machine, by using that current only, I'm just going to excite your field winding. So initially, without any, though there is no field current through the field winding, though there is no current through field winding, some flux should be there in that field winding. That flux can be called as residual flux. Okay, residual flux is a mandatory in self-excited DC generators, nothing but shunt series compound. Whereas residual flux is not necessary in separately excited DC generator. What is the reason for that? I already told you. In a separately excited DC generator, we are having separate DC source for the field winding, so that there is no need of residual flux in a separately excited DC machine. Whereas in self-excited, definitely we need residual flux. Let us assume that initially, let me take one color. So let me take here. Okay, let me take a blue color here. So let us assume that initially some residual flux is there. So let me take this one as residual flux pi RES. So please guys try to understand what is the definition of residual flux means what? Though there is no field current, though there is no current through field winding, some flux will be there in that field winding. That flux can be called as residual flux. Okay, so that flux is a mandatory in a self-excited machine, without which generator will not induce EMF. I'll tell you how. See example, see if some residual flux is there here, some small amount of residual flux is there here, because of this small amount of residual flux present in field winding. Now let us we'll have generator action. What is generator action? When a moving conductor, we know already we are placing armature winding on the rotor. We are placing armature winding on the rotor. If you provide mechanical energy for that armature winding, that means if you move that armature winding, when a moving conductor cuts this residual flux, some small amount of EMF will be induced. Because of that EMF, some current, I can say example IA current is coming here. It will divide as ISH and IL, load current and so shunt IS means field current, shunt field current, and IL means load current. Okay, so now suppose here one thing is very important. So sometimes though residual flux is there, Then also, self-excited DC generator will not build up the voltage. Very simple reason for that is, though residual flux is there, so armature terminals should be properly connected to field winding terminals. Okay, what is that? Armature terminals should be properly connected to field winding terminals. Let me take here. Suppose here, let me take terminals A in armature. Let me take A, and here field winding terminals should be equal to, I can say, F, and it should be FF. That means A should be connected to F, AA should be connected to FF. So then only, though residual flux is there, then EMF will build up. I'll tell you how it is possible. So example, if you see here, because of small amount of residual flux, so because of generator action, some EMF is induced here. Because of that EMF, some current IA is coming here. It is dividing as IS and ISH and IL. Whenever IS is coming like this, so please try to understand your ISH is entering at F. Do you agree or not? Please try to understand clearly. Your ISH is entering at F. Okay. So please try to apply right hand thumb rule. In right hand thumb rule, your thumb indicates direction of current. That means you have to show thumb downward direction, and remaining rapid finger shows direction of your shunt flux, which is from left to right. Do you agree or not? Please try to apply right hand thumb rule clearly, and please conclude that we'll get a shunt flux in the direction of residual flux only. Please try to show right hand thumb rule clearly. Your thumb should be downwards. And remaining rapid finger should show your direction of your shunt flux. Okay. So whenever pi rs, when residual flux and the shunt flux are aiding with each other, then flux will build up here, EMF will build up here. So once again, EMF will build up, IA will be increasing here, ISH, IL. This process will go on up to your load voltage. Whatever load voltage is there, up to your load voltage you are getting. So up to that, this process will be going on. Okay, guys. So try to understand. So very important point here is, first point, what are the conditions for buildup of voltage in a self-excited DC generator means there should be residual flux in the field winding, without which EMF will not be induced. Okay, guys. So first of all, tell me what is the definition of residual flux? I'll tell you. So tell me what is the definition of residual flux? Residual flux means though there is no current through field winding, some flux will be there in that field winding. That flux can be called residual flux. It will be very less, around 5 to 10% of your total flux. Okay. So there should be residual flux in the field winding, without which EMF will not be induced. And second point is very important. Suppose though residual flux is there, so your armature terminals AA should be properly connected to field winding terminals F and FF. Okay, so then only EMF will build up. That means flux will build up, flux will add, so EMF will build up. So that the process will goes on up to your load voltage remains constant. Okay, so guys, second point, armature terminals should be properly connected to field winding terminals. Okay, so suppose if you are not connecting armature terminals properly to field winding terminals, so what will happen? So to be frank, instead of shunt flux aiding residual flux, shunt flux will be opposing your residual flux. So because of that, residual flux will be nullified. So try to understand. Initially, small amount of residual flux will be there, but because of improper connection, because of not connecting armature terminals properly to field winding terminals, instead of shunt flux aiding your residual flux, shunt flux will oppose the residual flux. Thereby, residual flux will be nullified. Okay, so that is not desirable. So please be careful. Second point is very important. Armature terminals should be properly connected to field winding terminals. I'll show you. So how, if instead of connecting A to F and AA to FF, suppose if you connect A to FF, AA to F, what will happen? Let us see. So example, here only I'll see here. See, let me take the same thing here, armature, and here I took here A terminal here and AA. Okay, and here I told you shunt field winding having resistance RSH and some variable resistance connected here. I call that variable resistance as what? RF. and I had given nomenclature for these terminals as F and FF. Okay, and here let me have some variable resistors. Okay, so I told you instead of connecting A to F, suppose if you connect A to FF and AA to F, AA to F. Let us see what will happen in this case. Let me connect as your load resistance. Let me show as it is. So let me show load resistance as it is. Okay, right. Now let us see. So initially what we assumed residual flux is from left to right, right? So let me take once again residual flux from left to right here. Yes, residual flux is from left to right I taken. So that means I satisfied first condition. What is the first condition? There should be some residual flux. Yes, I got residual flux here. But the problem is I am not following second condition. What is the second condition? I am not connecting armature terminals properly to field line terminals. Because of that, what will happen? Let us see. Okay. So guys, I told you because of some small amount of residual flux. So whenever Z action will take place, this moving conductor curves that small amount of residual flux, some EMF will be induced. Because of that EMF, you'll be getting a current IA. It will divide as ISH and what? IL. IL, okay? But the problem here is your A is connected to FF here. So IS is coming like this, okay? And it is entering at what? FF. Previously it is entering at F. Now it is entering at what? FF. Okay. Because of IS is entering at FF. Now please once again apply right hand thumb rule. In right hand thumb rule, your thumb should be in the direction of your this blue color arrow mark, nothing but upward direction. So what will happen to your shunt flux? Please try to apply right hand thumb rule clearly, and please tell me what is the direction of shunt flux you'll get. It will be from right to left. Okay guys, so please try to apply Fleming's right hand thumb rule clearly here. So IS it is coming, it is entering at a FF. So if you apply right hand thumb rule, thumb indicates direction of your is a blue color arrow mark upward direction. So your wrapped fingers indicates direction of shunt flux, which is from right to left. So try to understand here, what about pi SH direction and pi RS? It is opposing, right? Your shunt flux is opposing your residual flux. Whenever shunt flux is opposing residual flux, your residual flux will be nullified. Residual flux will be nullified. This is very important here. It will be nullified. Okay. So now my question is, suppose initially I'm having residual flux, but because of improper connection, your shunt flux is opposing your residual flux, thereby your residual flux is nullifying here. Now, can you please tell me how you have to re-establish residual flux in that field winding? That is my question. Try to understand clearly. If shunt flux is opposing your residual flux because of improper connection, so residual flux will be nullified. Here my question is, how you have to re-establish residual flux in that field winding? Very simple. That is possible by using, what is that? Field flashing. What is that? Field flashing. Field flashing. Okay guys, field flashing. Very simple. Field flashing is very simple definition I can give like this. So whenever, because of improper connection, if pi S is opposing your pi RS, your residual flux will be nullified. So at that time, so please try to disconnect this field winding. Please try to disconnect field winding from the circuit, I can say from the armature. So just disconnect this field winding from the circuit and excite that field winding with a small DC source. I can say with small DC source for some time, small DC source for some time. Okay, so that the residual flux will be nullified once again. So residual flux will be re-established once again. Is it clear for you guys? Whenever residual flux will be nullified, so at that time, if you want to re-establish residual flux in that field winding, simply disconnect that field winding from the circuit and connect it across a small DC source and excite field winding for some time, so that residual flux will be re-established. Okay, this is a process. This entire process can be called as field flashing. What is that field flashing? Process of disconnecting field winding from the circuit. Process of disconnecting field winding from the circuit and connecting it across some small DC source and excite it for some time to re-establish residual flux in the field winding is called field flashing. Okay guys, so please let me erase this small portion here. And let me write definition for field flashing here. So I'm just writing definition for field flashing. Okay, Field flashing. Please let me write. Process of disconnecting field winding from the circuit. Process of disconnecting field winding. Process of disconnecting of field winding. I'm just writing simply FW. Okay. Process of disconnecting field winding from the circuit. And connect it across small DC source and excite it. Excite it means what here? It means I can say field winding and excite it for some time to re-establish residual flux. Residual flux is called, I can say simply field flashing. It's called field flashing. Okay, guys. So will be important for some interview point of view. They may be asking this question. What is about field flashing? Is very simple definition. I can give like this. Okay, right. Now, please. This is about your first point, second point, guys. And what about third point? This third point is very important. This is regarding critical field resistance. Okay, critical field resistance, or simply sometimes we'll call it as critical resistance. For explaining that, please let me show you open circuit characteristics, or I can say no load characteristics of a DC generator. So it's a graph between simply E versus IF. We know, guys, E equals to what is the formula? Generally pi Z N P by 60A. Okay, 60A. Here pi means flux, average value of flux per pole. E means EMF, average value of induced EMF. So Z means total number of conductors, N means speed in RPM, P means number of poles, A means number of parallel paths. Okay, already we know number of parallel paths equals to number of poles for lap winding. A equals to 2 for wave winding. So here my question is, suppose once design is completed, if your number of conductors are constant, and suppose if poles are constant, if number of parallel paths are constant, if I maintain same speed, if I maintain constant speed, that's very important. If I maintain constant speed, so at that time E proportional to, I can write simply flux proportional to field current, I can say IF. So guys, ultimately E proportional, what I can write? IF, right? So E proportional IF is a relation. So if you increase IF value, EMF will be increased. So what is the shape of curve we are going to have here? Something but linear, before linear. This is the curve actually before saturation. So but if before saturation is linear curve, okay, but after saturation, I can say, I mean to say that after saturation, so don't expect that if you increase field current, your EMF will increase. To be frank, because of saturation, there may be chance of reducing your EMF value also. So shape of EMF will be non-linear curve, non-linear portion. Okay, right. That's why you are going to have a curve like this. If E versus IF, if you draw, before saturation is linear, and once it enters saturation, it will be non-linear like that. Okay, guys. So this one I just explained here. Okay, so this only I just drawn here. Please try to see your red color waveform. So red color graph, you can understand. Red color graph, guys. Red color graph. Okay, red color graph. But the thing is, here, if you observe clearly, here whenever field current F equal to 0 here, I just showed E equal to 0. To be frank, E is not equal to 0. Practically, I told you already, though field current equal to 0, some small amount of flux will be there. That flux only we call it as a residual flux. Though field current equal to 0, some flux will be there. That flux can be called residual flux. Because of the residual flux, whatever EMF we are going to have, that EMF can be called as what? Residual EMF. I can write simply this one as residual EMF. Okay, residual EMF. Okay. So that's the reason why I'm just showing some small value. I'm just showing small amount of EMF. I'm just showing here this much EMF. So though field current equal to 0, I'm just showing why small amount of EMF means that EMF only we call it as residual EMF. Okay, guys. And one more thing, don't expect that. Suppose I told you E versus IF graph means initial though field current equal to 0, some small amount of EMF is there, that is okay. And if you increase your field current, don't expect that your curve will start increasing from this point only. No, because of a magnetic inertia, it won't respond up to one particular value of field current. After reaching one particular value of field current, it will start responding. That's why graph will not be like this. You will be having some curvature like this. Then your graph will start like this. Okay, guys. That's the reason. If you observe clearly your red color waveform, initially you are getting some curvature here. After reaching one particular value of field current only, so then because of magnetic inertia, you are getting this curvature part, and after reaching one particular value of field current, then magnetic inertia will be overcome. I mean, magnetic inertia was extinguished. So thereafter, if you increase field current, as I told you, you are going to have a linear curve. Yes, see, linear curve. You are going to have a linear curve here. Let me use laser point so that you will have some clarity. Yes. So though field current equal to 0, some small amount of EMF is there. That EMF I call it as residual EMF. And I mean, after zero field current, if you increase field current, don't expect that your curve will start from this A point only. It won't be like this. So because of magnetic inertia, it won't respond up to one particular value of field current. So because of that, you are getting some a curvature path like this. Yes, they are getting curvature like this. Okay, and after reaching one particular value of after reaching one minimum value of field current, then only your E value will be increasing like this. Okay, guys, it is increasing like this, and before saturation, it is linear, and whenever it enters it enters into saturation, curve will be non-linear like this. Non-linear. Before saturation is linear. After saturation it is a non-linear. Okay, guys. Now here, so I think I explained only red color graph here. Let us see what is this RF1, what is this RF2, what about this RF3, what about this RF4, all those things. So this is regarding your variable resistance, whatever connected in the field circuit. Please try to understand here. Initially, suppose by varying this field, by varying this variable resistance RF, okay, I just kept total field circuit resistance. I just kept as RF1. So example, I just kept RF1. Okay, RF1. So at that time, if you see this RF1, if you see this RF1 is touching your OCC curve at one particular point. Regarding this, whatever EMF I call it as, it is nothing but EMF E1, EMF E1, EMF E1. Suppose, guys, if I increase field circuit resistance from RF1 to RF2, it's a common sense. I think you only will tell. Whenever field circuit resistance will increase, what will happen to shunt current? Or what will happen to field current, shunt field current? It will reduce, right? Whenever field current will reduce, what will happen to flux? It will reduce. EMF reduce. That's the reason why if you go for RF2, that is nothing but a yellow color case. If you take RF2, which is more than RF1, it is cutting your OCC curve at this particular point. So this EMF is, I call it as E2, which is less than E1. Which is less than E1. That means try to understand. As you are increasing your field circuit resistance, your EMF is reducing. Very simple reason. Because as you are increasing field circuit resistance, field circuit current will be reducing, so flux will be reducing, EMF will be reducing. So RF1 I explained, RF2 I explained. Let me go for RF3. So for RF3, it becomes just a tangent to this OCC curve. Have you please try to understand? This green color graph, whatever I just draw on RF3, it becomes exactly tangent to this OCC. So it is touching at this point. I call that EMF as E3 here, E3. Okay, which is less than E2, and E2 is less than E1. Very good. Okay, so now guys, suppose if you increase field circuit resistance after RF3 also, that means if you go for RF4, it is not at all touching your OCC curve. Try to understand, it is not at all touching your OCC curve. So okay, maybe it is touching very small in here, a small portion is there. This small amount of EMF, I can approximately take it as residual EMF, or I can neglect this one also. Nothing. Okay, nothing problem. So if you go I mean beyond this RF3 in our example, for RF4, so what about the induced EMF? It is almost all zero. I can say residual EMF or almost all zero EMF. So guys, please try to understand this RF3 only. I call it as a critical field resistance, or I can say critical resistance. Okay, critical resistance. Is it clear, guys? So tell me, what is the definition you can give for this RF3 critical field resistance? Very simple. The total field circuit resistance above which means you should think about RF4, above which EMF will not build up, or the total field circuit resistance below which EMF will induce. Yes or no? So what is the definition for critical field resistance? The total field circuit resistance above which EMF will not induce, below which EMF will induce. Okay, guys. So that only simply I wrote here. Please try to understand. The total field circuit resistance should be dash the critical field resistance for buildup of voltage. Tell me, guys, for buildup of voltage. So what I had to write in that blank? Please try to respond, guys. What I should write in this blank should be what? The total field circuit resistance should be dash than the critical field resistance, I'm saying, for buildup of voltage. That means when compared with the RF3, so for buildup of voltage, I should think about RF1 and RF2, no? That means what? The total field circuit resistance should be below critical field resistance for buildup of voltage. So please let me write here, the total field circuit resistance should be below the critical field resistance for buildup of voltage. Okay. So yeah, it is nothing but B here. So let me erase and write clearly here. Yeah. Please let me some other color. It is not visible. Should be below the critical field resistance for buildup of voltage. So I'm just giving definition for critical field resistance, same definition only, same point only. I'm just writing in a different way. Critical field resistance or critical resistance means total field circuit resistance above which EMF will not induce. Very simple. So previous I told below which EMF will induce. So above which EMF will not induce. That's it, no? Okay, very simple definition. So that is about a critical field resistance, or sometimes we'll call simply it as a critical resistance RC. Okay. Now, so let me discuss fourth point. So guys, as of now, I discussed 3 points here. First point, what I said, there should be some small amount of residual flux in the field winding for buildup of voltage, without which EMF will not be induced. And second point, armature terminals should be properly connected to field winding terminals for buildup of voltage. Third point, total field circuit resistance should be below the critical field resistance for buildup of voltage. Okay. Now I think in third point deals with the third point deals with the field circuit. Your fourth point deals with the load circuit. Please don't confuse. Fourth point deals with the I think load. Okay. So guys, before I explain fourth point, I'll ask you a simple question. Please try to respond. Suppose initially small amount of residual flux is there, okay, and because of the small amount of residual flux, because of generator action, some EMF is induced, okay, and because of that EMF, some current I is coming, okay, because of this I, it is dividing as IH and IL, okay, guys, please try to understand. Suppose if I keep very less value, if I keep very less resistance value in load circuit, if I maintain very low resistance in the load circuit, what will happen? Everybody knows that current always passes through low resistance. So obviously entire current will be flowing in the load circuit only. I think there is no current flowing in the field circuit. If there is no current flowing in the field circuit, if there is no ISH, if there is no pi SH, there is no building up of flux, there is no EMF buildup. Okay guys, so that means here some minimum value I have to maintain. Some minimum value of resistance should be maintained in the load circuit. Okay, otherwise if you maintain resistance value below that value, entire current will be flowing in the load circuit only. There is no current coming into the load circuit, field circuit. So there is no shunt flux, there is no buildup of flux, there is no EMF buildup. Okay guys, so please here you have to maintain some minimum value of resistance. That only I'm calling it as the RLC. RLC means what? Critical load resistance. Previously I told here critical resistance, RC. I'm discussing about critical load resistance. So please, what is the fourth point I can write here? The total load circuit resistance should be above the RLC for buildup of voltage. See, try to understand. This third point is somewhat different from the fourth point. So third point I'm saying here, fourth point I'm just saying here, the total load circuit resistance should be above the critical load resistance RLC for buildup of voltage. So what is the definition I can give for this critical load resistance? The total load circuit resistance below which EMF will not induce. So I told you already here you have to maintain some minimum value of resistance. If you maintain below that value, entire current is flowing in the load circuit only. There is no current going into the field circuit. There is no shunt flux. There is no buildup of flux. there is no buildup of EMF. So here some minimum value of resistance I have to maintain. That minimum value only I am calling it as a critical load resistance. So if you maintain resistance value below that RLC, EMF will not induce. See, critical load resistance, the total load circulations below which EMF will not induce. That should be above critical load resistance. The total load circulation should be above the critical load resistance RLC for buildup of voltage. So don't confuse this third point and fourth point. Okay. So it is regarding a field. Third point is regarding a field circuit. Fourth one is regarding a load circuit. Okay, guys. So don't confuse. So please try to understand clearly. There is some difference is there between third point and fourth point. Difference is there between this RC and RLC. If you observe clearly RC, the total field circulation should be below the critical field resistance for buildup of voltage. And what about fourth point? The total load circulation should be above the critical load resistance RLC for buildup of voltage. See, just somewhat different. No? And what about definition for critical field resistance? The total field circuit resistance above which EMF will not induce. What about here? For definition for critical load resistance, the total load circuit resistance below which EMF will not induce. Okay, guys. So very simple thing only. Please try to understand clearly. And what about last point, fifth point? Okay. So see, guys, what is the definition for generator reaction when a moving conductor curves the magnetic field? When a moving conductor curves the magnetic field, and EMF or current is induced in that conductor. Okay. So that means you have to provide mechanical energy for the conductor. That means you have to move the conductor, right? You have to move the conductor. But with what speed? That is very important. No? With what speed? You have to move the conductor with minimum speed. Suppose if it is very less speed, so EMF will not be induced, no? So that's what I'm saying. Speed of generator should be more than critical speed NC for buildup of voltage. That means that speed of the generator should cross this NC value. Then only EMF will start inducing. Okay. So don't say that when a moving conductor curves the magnetic field and EMF will be induced in that conductor means moving means if you are moving conductor with speed which is less than NC, EMF will not induce. You have to cross one particular minimum value of speed, nothing but NC. Okay. Then only after reaching your NC value only, your EMF will start increasing. EMF will start, I can say, build-upping. Okay. EMF will start inducing. So speed of generator should be more than critical speed for build-up of voltage. So what is the definition for critical speed? I can give I'm just giving just same statement only. I'm just writing like this: the speed of the generator below which EMF will not induce. Above which what will happen? EMF will induce. No, below which EMF will not induce. Same thing only. Okay, speed of the generator should be more than critical speed for build-up of voltage. Speed of the generator below which EMF will not induce. Simple thing only. Okay, these are the 5 points. And see, guys, in addition to these 5 points, some more points are there for conditions for buildup of voltage in a self-excited DC generator. Okay, so try to understand these 5 points. In the next video, I'll be discussing some more factors are there, some more points are there which are affecting conditions for buildup of voltage in a self-excited DC generator. That we'll discuss in the next video. Okay, guys, thank you.